So just a little bit in advance of what to expect. Essentially, this is 2 days worth of very intense, very detailed DNS material, so I'm certainly not going to be able to give you the level of detail. It's more to give you an idea of the incredible range of things that we are doing with and to DNS and how these folks deep dive into it. I would encourage you to go to the DNSOARC website where there are videos and slides for all of these talks to actually get a useful level of detail on them. So first, a little bit about OARC. It is essentially an attempt to have a place where people who go into DNS specifically to do research, to share data, do information sharing, shared experiences. We do 2 workshops a year where we do a 2-day set of talks, usually concurrent with NANOG or RIPE or IETF. There is a lot of analysis tools, data sets, tools, things that our members can have access to help them be a little bit more proactive and predictive about what they can do with their DNS services, both authoritative and recursive. Some of the things that have been useful to folks based on that, during large-scale DNS incidents, we have folks that are giving us data and sharing it. We have something day in the life. It's essentially the 24-hour packet capture of all of the authoritative traffic that we can have access to, particularly from the root servers. And all of those folks share that data. We use it to do capacity planning. We use it to do incidents and forensics. And there are mailing lists and other places where the various engineers can talk about these things and share in a somewhat more closed environment in much the same way that there are other vetted and trust groups for other forms of security in computers. So the conference that we just had finished yesterday. I'm still a little toasty. 2 days full of presentations, and we had 130 attendees, and that covered 68 different organizations that sent their engineers to that talk. And we've been averaging about 100 to 120 attendees for the conferences. And now I'm going to start going through some of the talks. So one of the things that is very prevalent in DNS right now is DNSSEC, secure DNS, where you have cryptographic signatures of DNS data so that you can validate that the DNS answer you got was what the zone owner wanted. And because it's crypto and we are now worried about things like DNS response sizes as a DNS amplification vector, people are looking at all the crypto algorithms because, like all algorithms, there are trade-offs. You can possibly crunch something or encrypt it faster, but it might either be bigger or decrypting it might be slower. You know, there are all the knobs and you have to decide which ones there are. There's one called elliptic curve that's getting a lot of interest right now because it's fairly cheap to compute, and it has significantly smaller signatures, so the DNS responses can have many bits and be cryptographically secure without having to have quite that much of a DNS payload. So problem is that if you want to be able to do that, you have to be able to use that algorithm all the way from the root through the TLDs like com or net or org to your second level domain and beyond. And if your algorithm is not supported by whoever is signing that zone at that hop, and or it's not supported by the folks that are running the recursive servers, your crypto doesn't decrypt, and you either get the choice of doing a downgrade attack or not giving an answer for that DNS. So they have been looking at how to do that, and unfortunately, the short answer on this particular one is right now, the TLDs and the root servers are not supporting this algorithm. And so this was really sort of a plea to, hey, can we get this moving? There's an awful lot of folks that really aren't supporting it yet, and that seems suboptimal. And so we were trying to proselytize for that. Another interesting challenge is when you do DNSSEC, you have to put a key into the parent zone of yours. So if I register example.com, I have to actually put records into com that you can use as a hash of my public key, so when you look at my data in example.com, you can actually go through and correctly validate that does mean that you need to put things into the registrar for the account. So if I move from GoDaddy to Dyn, I have to move stuff in COM by whatever interface they have. And there is no standard API for doing that. And so this is a whole series of experiences and a recommended RFC for essentially how you either don't have to take off DNSSEC from your zone or break it while you move it from registrar to registrar. Pre-deployment of DNS and testing. I love testing. There is a tool called DNSViz, and the URL for it is dnsviz.net, and it is essentially a graphical display of all of the steps in validation and whether they are working or not in nice pretty colors with cute little circles and lines and graphs, just like Alice's Restaurant. It's now being used offline where you don't have to have live data yet. The code has been released, so what you can actually do is you can point it at your stuff in your lab before you roll it out into production. So for a change, we are not using the internet as the world's largest beta test site. Anycast. As a routing crowd, you have some concept, I'm sure, of Anycast, where essentially I announce the same IP address in multiple places, and there are actually multiple servers that all have that address, and you go to the one that BGP or whatever routing protocol says is topologically closest to you. That is widely used in DNS, where we have, by definition, we hope, the same data in multiple places, and so it doesn't matter where you go to as long as you get there fast. It also allows for a lot of other things, including lowered latency because you can be topologically close. It gives a lot more DDoS resilience because they have to attack you in every AS that you're announcing this in and have actual boxes answering in. They don't have to get funneled to the one single place that you can go ahead and melt. It works well, like all techniques. It has trade-offs. And among other things, it's very interesting to debug because you got to 1.2.3.4 and it gave you an answer, but which version of 1.2.3.4? Was it the one in London or in San Francisco or in Australia? You don't know. So RIPE has a project called the Atlas where they have these little boxes sitting around in people's homes and in data centers and other places, and you can essentially rent time and use it as a test platform. And so this was a person who set up tests to essentially test how well things worked and used the right probes to see if it really worked well. And what they more or less came to the conclusion was it's mostly working, at least for root servers. 12 instances seems to matter. Where you go in the network seems to matter. Not having two root instances in the same data center is probably a feature. Another concern that has been very big in the IETF and in Nanog and RIPE and various other places post-Snowden is privacy. And while DNS data is probably better classed as metadata, we all know that even metadata exposes more than we would like. And DNS, much like SMTP, was originally designed to be completely open, completely unencrypted, and is a nightmare in security. And so this goes through a whole series of potential techniques in how to, even when you encrypt the data, to expose even less of it so that even traffic analysis gives you less valuable information. It's very early work, but some clever research. This particular CVE, this was the glibc bug, which essentially allowed you to, at your leisure, remotely, with very little effort, crash anyone's name server. If they were running the wrong code, there are a few other things, but it was trivially easy. And so most of us spent a very horrific week or three patching desperately to get ahead of all of this. This was an analysis of the actual code itself, a deep dive into what really is the bug. How do you know? How do you remediate it if you can't actually go through? And what does it mean and not mean? It was an excellent presentation. Someone also, one of the TLD operators and ccTLD operators wanted to know if they could look at their authoritative server and figure out who was asking them questions. Was it a large recursive cache of an ISP? Was it individual clients? Who was it? And potentially, if they could figure that out, they might be able to treat them differently in order to improve performance and redundancy. And so they went through and did more or less big data crunching and statistical, and threw some machine learning and some other lines in. This was one where I certainly didn't do terribly well in stats in college, but learned a lot of interesting things about what was and was not useful information in being able to make those kinds of decisions and do traffic analysis. And more DNSSEC. So DNSSEC works by having what's called a key signing key, which its purpose in life is indeed to sign keys. So what it does is it signs the zone signing key, which is the key you use to sign the records within the zone. And it's a whole chain of those. So the key signing key gets hashed in the parent zone. When you make the delegation, there's an entry point where you look at the actual KSK in the child, you look at the hash of it in the parent, and if they match, that link validates. You can then use the key signing key to validate the zone signing key works. Then you can look at the signatures within the zone, and you can validate. The 3-second version of DNSSEC. You have to start somewhere at a root or a start of the trust anchor chain. And for us, that means that there is a key signing key that there's no parent zone for because it's the root. So how do you validate it, and how do you get it to other people securely when you need to roll it? And so VeriSign, as one of the root operators, has been studying what to do and how to change that key signing key without breaking DNSSEC in the internet. And this was basically a breakdown of what are the operational impacts, and which fairly obviously, if the key signing key for the root breaks, all DNSSEC ceases to function. Anybody who assigns zones and uses any one of a number of large DNS resolvers, including folks like Google, Comcast, all of those zones go dark. So obviously we're all very concerned about that working. This was the breakdown of the schedule of what they're doing in which order, and why we should all feel warm and fuzzy that it will follow. And also asking folks to look very closely at an RFC 5011, which is an automated and secure way of getting that key without you having to have some person actually go into some zone file and, God forbid, actually do something like pull a file in VI. Second level domains, so example.com. We also want to be able to test those and their performance just like we test the root servers. And so at this point, there are a huge number of name servers doing all of this. A bit of DNS esoterica. Glue records are things that is in the parent because it's referred to in the child. So if I do ns1.example.com as my name server, and you go to com and say, what's the IP address for example.com, you have no way to get there. So glue records allow you to duplicate and put ns1.example.com into the com domain as an A record, so you actually get an IP address that you can then go and ask, what is the name server for, and follow through. There's a lot of cruft in .com and the other TLD files. And so this was basically an interesting analysis of what kind of cruft was in there, what kind of legitimate stuff was in there, and what kinds of things were being used commonly and less commonly. Hunger for Quades, this was an analysis of essentially an inadvertent failure. There is a company that had a box that did cloud backup, and it would ask for certain things, and if it didn't get an answer, it would ask rather aggressively. One of the fun things if you are a DNS vendor is if all of your authoritative servers become unreachable because you didn't engineer well, recursive servers are going to just go through and fail. Oh, actually, no, this is the... sorry, wrong talk. This was the one... they were going through things where ccTLDs did not have quad A's for all of their name servers. So this again gets into, there's an effort to do happy eyeballs, something where we want to give some preference to v6 and use v6. DNS is interesting in that the transport you use to ask your questions can be v4 or v6. The data that you ask for can be v4 or v6, and they're not tied. But in a perfect world, very important name servers should be dual stacked and should be available in both. In this case, what happened was, because of the way they did things with v6 connectivity, they wound up doing an awful lot of v4 transport answers over a link that cost more money. PCAP to HDFS. So when we're debugging DNS, like everything else, frequently there is no substitute for actually looking at raw packets. But DNS is UDP and stateless because there's a lot of packets. You can have hundreds of thousands of these things floating through in a very short period of time. That's a lot of data. And so basically, the Canadian provider, or the ccTLD there, wanted to be able to do analysis of a lot of stuff. They basically break through how they do things with a Hadoop cluster and some machine learning to actually get through and have the utility of PCAPs without the space. An amusing little, this is how you can do non-printing character domain names and the fun you have. IDN, international domain names. It's a fascinating little exercise to show just how damn stubborn we are at doing things that we really don't need to do. Okay, this was the surf fail. This was the one that I dived into a little early. The problem was that there are a whole series of these boxes that apparently, even if you don't sign up for the cloud service, they will still do a health check forever, and you cannot disable this. And they apparently did a really bad job at engineering their name servers so that they managed to knock all of them off the internet. What that means is that all the recursive servers suddenly get a serve fail. It's the something went wrong and I can't get you an answer, so that's all I can tell you. It became enough of a load that it basically became almost half of their recursive traffic retrying all of this futilely because it was never going to work. And because it was a serve fail and not NX domain, it's not a hard failure, so they don't cache the fact that, oh, I'm going to wait some period of time before I even try again. So unfortunately, there are not a lot of resolvers that are overly helpful, and it puts a huge strain on the infrastructure. Yeti is a project that is interesting because breaking the root servers is a bad thing. But there's a lot of stuff that we'd really like to be able to know about the root servers. It's hard to do in the labs because you need to be widely distributed, you need to have a very wide client base. So essentially what it came down to is, how do we have something that looks and smells and acts more or less like the root server infrastructure without having to break the infrastructure to do it? And the Yeti project was spun up to do that. And so basically what they have is they have the root zone, but they change the IP addresses of the servers to their own servers and then leave everything else within the zone data alone. And then they run experiments. And in this case, what they were doing was what happens if the zone signing key for the root zone, if we have multiples of them? Does it break anything? What happens if we put out a big zone signing key? Because recently we upped the size of the keys, how many bits we use to encrypt with our key signing key and zone signing key. And what happens with a KSK and a rollover? And this was this experiment and the results and lessons learned. Anycast and DDoS. Anycast is a very good defense in a lot of ways. Like I said, it increases your attack surface. They have to have bots in multiple ASs to attack you if you are in multiple ASs. At this point, all of the root servers are now anycasted. There was one that hadn't been anycasted up until recently. At this point, there are 13 letters, but that's actually every single one of those, which gets down to an IP address, v4 and v6, is a few to dozens of Anycast clusters scattered around the world. However, there was an attack last year that hit one of the root servers. this is normally not a problem because that's why we have 13 letters, so that if you can't reach one, you just switch over to another. And we have fairly long TTLs, a couple of days, as I recall, once you get an answer before you ask again. But when you start having that, and when you are anycasted and you're noticing that you're under attack, what do? Do you try and shift traffic? How do you decide where to shift traffic? Do you leave it alone? Do you deliberately decide that this small hub with a small number of customers gets sacrificed so that you don't completely lose all capability? And so this paper was a breakdown of the choices, the issues, and what you would need to do to intelligently make that kind of decision for your infrastructure and your Anycast. So this was another in the how do we get the root trust anchor, the key signing key securely. And this was someone who decided to write it in Python and do all of the various steps. And they broke down, how do you know where to get it securely? How do you know it really is the correct key? How do you ram it into your automation and go through? And they have code as a sample. All right, and another DNS esoterica alert. ENT is not ear, nose, and throat. It is something called an empty non-terminal. So if I have a.b.example.com and I am doing DNS correctly and following all the rules, I have created a zone b.example.com. And within that is some kind of DNS label A with an RR set that corresponds to that. However, we have been allowed to be lazy and sloppy for decades now, and pretty much all of the authoritative name server software allows me to put a.b into the example.com zone. You don't know whether or not a.b.example.com is a correct set of 3 zones and 1 single label, or if it is what's called an empty non-terminal, because B is empty. It's not a zone. And it's non-terminal because there's stuff that should have been in the zone B, the label A. That is an empty non-terminal. DNSSEC is an interesting exercise because many of the things that we got away with in breaking the rules for decades are wrong and are insecure. Because one of the things that should happen is there should be that zone ba.example.com, which should include key signing keys and zone signing keys, and should have a hash of that in the example.com file. So if I'm trying to validate that a.b.example.com works and is cryptographically correct, I have to actually do all of that work. Because there is no b.example.com and none of the labels with that, all sorts of other things, including proof of non-existence, NSEC or NSEC3 records, all break. There is also, as we're going through and now trying to clean up code, all sorts of other side effects of various things that go through. And so this is a breakdown of what a French agency found out, including some things like that Google had actually done what they were supposed to and followed the rules, and because of the way they did things, that just broke, and Google validates. So that label was unusable. And they came up with an interesting hack, which is putting in a text record in the right place to sort of mask the fact that there's an empty non-terminal. And that allowed the signatures of non-existence, or the NSEC records, to do more the right thing. There was a very interesting presentation on what happens when you are trying to decide for yourself whether you want to use a certain provider as the person to own the zone files for you and do your authoritative DNS, or you are running authoritative DNS and someone wants a disinterested third party or third parties to actually watch. And so what this was a breakdown of a whole series of how do you measure, what do you measure, what are the trade-offs, who do you look at, who do you compare to, how can you come up with essentially being an informed consumer, or be able to say to your customers, You may have seen something weird, but here's what not only me, but everybody else who measures and watches me saw, so it's probably something else. So that is, in a nutshell, what was covered. As I said, that is now 2 days worth of detailed talk, so please go to this website. It has a link to the conference, which has videos, it has slides. The other is that it has information on future conferences and on membership. If you decide that DNS data is something that is vital to your company and you would like to be able to share with other professionals, all the information's there. So at this point, I open up for questions or let you move to your peering tracks.
Hey, Paul.
Hey.
Joe Provo, Google. Yes, I will dig into the site to see all the detailed data, but one thing that seemed to be relevant to this crowd, out of the DDoS and Anycast topic, can you just briefly say whether or not the discussion of status notifications or otherwise getting information out to the affected population was covered?
We really didn't talk about notification, and that is definitely difficult, because one of the problems is that if you Anycast, you are peering with people with which, in many cases, you have no existing relationship whatsoever. In my day job, trying to find the right NOC to talk to, we are reduced to essentially sharing the electronic equivalent of a Rolodex once we get a useful number. Now, there are some mailing lists, including one run by DNSOARC, that has one of these trust groups. So one of my tools that I have used for that is, hey, does anybody have a contact at? Other questions? All right, well, if not, thank you very much.